So looking at compounds, we know that compounds are made up of individual elements, and that therefore each compound can be formed by a synthesis reaction of its constituent elements. So suppose that we're trying to produce H2O, it's a compound. One way of doing that is by doing the synthesis reaction of its two elements, hydrogen and oxygen. And so we have H2 plus O2, balance out that equation, and then we've got a synthesis reaction for water. Now, with that equation, we could go ahead and find the enthalpy change for that particular reaction. And that particular enthalpy change has sort of a very special term that's used for it here because of the fact that this is a synthesis reaction for a particular compound. And so this is called the standard enthalpy of formation. And so standard enthalpy of formation, we'll give it by this sort of delta H with a little subscript F and our little sort of degree symbol naught up at the top right here, so delta H F naught. This standard enthalpy of formation is the enthalpy change for a reaction in which 1 mole of a substance is formed from its individual elements in their standard states. So whenever we have this formation of H2O right here, it's basically saying, hey, if I was forming this from its original elements and I was producing 1 mole of this H2O that's right here, what would be the enthalpy change for that, or the heated reaction for that particular reaction? What would delta H be? So note though that it says individual elements in their standard states. We need to talk on that a little bit. The standard state of a substance is its most stable pure form, and that's going to be at a pressure of 1 atmosphere and a temperature of 25 degrees Celsius, okay, at those under those conditions. So we're looking at 1 atmosphere of pressure if it's a gas, and for all substances a temperature of 25 degrees Celsius. And what is that substance's most stable pure form? So for a pure liquid or a pure solid substance, the standard state is the most stable pure liquid or solid. So for a gas, that standard state is the gas at 1 atmosphere of pressure, and for a substance, this is an aqueous solution, the standard state is going to be at a 1 molar concentration. So let's look at some examples of how would we identify that standard state. So what are the standard states of some of the following here? So our first one is H, hydrogen. So our question is that at 25 degrees Celsius and 1 atmosphere of pressure, what state would hydrogen be in? Well, first thing, we know that hydrogen is one of our diatomic elements, and so it's not going to be H right off the bat. It's going to be H2. Second question is going to be, what is the phase? So if it's 25 degrees Celsius, we know that hydrogen at that temperature would be a gas. If you didn't know that, you would need to look up for H2, for hydrogen gas, what is the freezing point, what is the boiling point? And if you look at hydrogen gas, you'll see the boiling point is far, far lower than 25 degrees Celsius, which would mean it's going to be a gas at 25 Celsius. And because of that, the standard state of hydrogen is H2 in gaseous form. Next one would be H2O. And so if we asked, while it's not an element, we can still talk about its standard state. So the standard state of H2O, of water, is going to be, what is water at a temperature of 25 degrees Celsius? And we know that 25 degrees Celsius, water should be a liquid. And so it'll be H2O liquid in this form. Next one is argon, Ar. Is its most stable form just Ar, or is it something like Ar2 or Ar3? Well, it's argon. It doesn't end in Gen or ine. It's not diatomic. So its most stable form is going to be just the Ar right here. The phase is going to be a gas because we look at the boiling point of argon, it's well below 25 degrees Celsius. Next one, NaCl. And so if we're talking about what's the standard state of just NaCl, we'd first say just the pure form of NaCl, the pure form of sodium chloride, is going to be basically regular table salt. We're not mixing it with anything else based on what it says here. And so at 25 degrees Celsius, your table salt is definitely a solid. So we're going to say it's in solid form. Now, our next one is we're going to take that same sodium chloride and we're going to say, well, what would the standard state be if instead of being pure, just the pure substance here, what if it instead was in a solution of water, where water is going to be our solvent? So if that happens, then we're not looking at the solid form, we are looking at the aqueous form of NaCl, and the standard state of any substance in aqueous solution is going to be 1 molar. And so this would be 1 molar NaCl, and then we have to indicate that it's an aqueous solution in this case. So you can have standard states of a substance that is in pure form and one that's an aqueous solution. It is okay to talk about those. And so that would be sort of how you'd identify the standard state. Look at what is it going to be at 25 degrees Celsius. If it's a gas, what would be at a pressure of 1 atmosphere, which right now is not really going to make a big difference in terms of what we're talking about here. We're just going to look at that temperature more than anything else, and we'll look at the molarity if it's an aqueous solution. Now, if the substance is an element in its standard state, then by definition, its standard enthalpy of formation is 0. Okay, so if we're looking at these and saying, well, which of these right now do we know what the standard enthalpy of formation is? We say, well, which of these are elements in their standard states? So we look at first is H2. Is that an element? Well, yeah, it's just pure hydrogen. Even though it's sort of molecular hydrogen, it's still the pure form. It is the standard state of hydrogen in general. And so for that, we would say our delta HF is going to be equal to 0. What about H2O? So do we know what the standard enthalpy of formation for that is? Well, it is in its standard state, but it is not an element, and so right now we haven't figured that out yet. Okay, argon gas. So because of the fact that argon is an element in this case, it is in its standard state, then we would say that delta HF naught is going to be equal to 0 for that one right here. For NaCl and for the solution of NaCl, we do not know what it is right now. We don't have a way of figuring it out because it is not an element in its standard state. But for elements in their standard states, then we know the standard enthalpy of formation is always going to be 0 kilojoules per mole. So what if it's not then? So that gets to our last point. If the substance is a compound in its standard state, its standard enthalpy of formation is equal to the enthalpy of reaction for its synthesis reaction of elements that are at their standard states. So let's say that we're trying to figure out CH4. And we want to know what is the standard enthalpy of formation for that substance. Well, the way you'd figure it out is you'd say, well, what synthesis reaction would produce CH4? Well, to produce CH4, then we'd have carbon plus hydrogen gas, right? And then that would produce CH4. And so to do this, that we'd say, well, first, what are the standard states? Well, carbon is at room temp at 25 degrees Celsius is a solid, and so we'd say it's going to be the solid form of carbon. And just as an aside, carbon actually has 2 different solid forms. It has graphite, like you use in your pencil. Most pencil letters are made of graphite. And the other one is diamond. Now, of those 2, they're both pure forms. They're both at 25 degrees Celsius. For this right here, the more stable of those 2 is graphite. So in this case, this would be graphite if we were really doing this reaction. Typically, when I give you substances like that, if it has another form that can be in, that's another what's called an allotrope of that substance, that I will give you the most stable form if I give you what the standard enthalpy of formation is. H2, we said before, is the standard form is going to be a gas, and then for CH4 is methane. That's also going to be a gas at 25 degrees Celsius. So if I were to take this reaction here, the solid form of carbon plus the gaseous form of H2 yields CH4 in gaseous form here, and I were to find what the heat of formation is for that reaction. And so if you look at the bottom, I've actually given it to you. Delta H naught is equal to negative 74.8 kilojoules per mole for that particular reaction. That means that the heat of formation is equal to negative 78.4 74.8 if I could read correctly, 74.8 kilojoules per mole. So all you have to do if you want to figure out what is the standard enthalpy of formation is figure out what is the standard enthalpy of reaction of the synthesis reaction to produce it here. And I did leave out the 2 to get that balanced right there. So that's how you'd go about figuring that out. Now, for most substances, we don't really have to figure it out. The standard enthalpy of formation has been determined by experiment or by calculation from the strength of its internal bonds. And so these values are typically available in reference tables. And so you can see an example of that right here. So if you were ever needing to do something, you said, well, what is CH4? Then you would look it up. And so we look down here, we look for CH4, and it's a little hard to read on here, but CH4 is right here. And if you look over here, it says negative 74.81. And so we can look that value up most of the time. You will have a table provided to you with, for a lot of common substances, what their standard enthalpies of formation are. Now, let's apply this to Hess's law. Because remember that according to Hess's law, the enthalpy of reaction for any reaction is the same, no matter if a reaction is one step or many steps. So we can use that by taking a reaction, we can say write it out in the terms of several other reactions that would lead us to the same products from the same reactants. And we add those up in the right way using Hess's law, and we can end up figuring out the enthalpy of reaction. Now, one possible way that any reaction could be many steps is if all of its reactants were decomposed into their individual elements and then all products were then synthesized for those elements. Let's look at an example. So suppose that we have this reaction right here. C2H4 plus H2O yields C2H5OH. Well, this C2H4 that we start with, we could just take that and break it up into its component atoms. 2C plus 2H2. Well, those are the elements in their standard states. Carbon is going to be a solid at standard state, hydrogen is H2 in the gaseous form right there. So we've taken that carbon, we've broken apart its bonds. The next one is going to be the H2O that we start with. Well, we can do the same thing. We can take that H2O, we can break it up into its component elements, 2H2 plus O2, just like that. Similarly, we could take the C2H5OH and we could put it together, we could form it in a synthesis reaction from its component elements here, from carbon and hydrogen and oxygen gas. Now, for each one of those, since those are synthesis reactions, our overall heat of reaction for each one of those is going to be the same as the standard enthalpy of formation for that substance. So if I want to know, hey, what is this delta H naught for this particular reaction, I would just look up what delta HF is, what the standard enthalpy of formation is for C2H5OH. By getting that, that's going to let me figure out what this delta H naught is for this reaction. And I can do the same thing for each one of these. Now, in two of these are decomposition reactions, so I'd have to flip the sign on it because it's backwards, right? This is for these standard enthalpies of formation are for a synthesis reaction, not a decomposition reaction, but it still works the same way. I can get all those values pretty easily. So unlike all these previous cases with Hess's law, where what we've had to do is we've had to be given what our individual steps enthalpies of reaction are, now we can look up those in just a standardized table. So it actually goes even farther than that. If we look very carefully, then we can see if we use Hess's law this way, it simplifies even farther, which is a great thing. So it turns out that the enthalpy change of reaction is simply the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. So if we were to take the enthalpies of formation for each of the substances that are the products that we end up with in the reaction, we add all those up, and then we take all the enthalpies of formation that we look up in the table for each of the reactants, no matter how many we have, and we add those up, then we just take the difference between those two, as long as you take each one times the number of moles each one has in the reaction. So if we wrote this out in terms of more of a traditional formula, we would say that delta H, oops, that doesn't go there, that delta H naught right here for any reaction is going to be equal to the sum. And so remember, this little letter right here from math is a Greek letter sigma, capital letter sigma, means the sum of is equal to n times delta HF naught for the products. And so that n right there is the coefficient for each of the products. So if we were doing, say, 2H2 plus O2 yields 2H2O. What we would do to figure out this piece right here is we would say, well, what are the products? Well, we have H2O. So we look at our table and look up what is the standard enthalpy of formation for water, and we'd multiply that times the coefficient, which is 2. And that number is going to go right here because that's the only product we have. Then we'd subtract off the sum of the coefficients times the enthalpy of formation for the reactants. And so we got two reactants here, H2 and O2. And so for this section right here, we're going to drop it down. What we would do is we would add up the parts. We would say, hey, as we've got 2 times whatever the standard enthalpy of formation is for H2, which actually, in this case, we we know what that is. That's going to be 0 in this case because it's in pure form, right? And then we could do the same thing for our O2, is that we would add up, in this case, 1 times, in this case, it's going to be 0 over here for the oxygen because of the fact that the oxygen is in pure form. It's in a standard state. And so that's all you really do is you take the coefficient times the standard enthalpy of formation, the coefficient times the standard enthalpy of formation, the coefficient times the standard enthalpy of formation, and you add up all those values for your products, and you add up all those values from your reactants, and you take the difference, do the sum of the products minus the sum of the reactants, and if you do that, that will give you delta H, delta H naught. What is the enthalpy of reaction, the heat of reaction for that reaction? So let's look at an example of this, make it a little easier to understand. So find the standard enthalpy of reaction, the enthalpy change for the following reaction: C2H4 in gaseous form plus H2O yields C2H5OH. So remember that we could do this with Hess's law by doing a decomposition reaction of our two reactants and the synthesis reaction of our product, or we could use our new summation formula here. And so let's try out using that formula here. So what it says is the sum of the coefficient times the products minus the sum of the coefficient times the reactants is going to give this to us. So let's look first at what the products are going to be. And so I'll do a little bracket so I can bracket around each section just sort of like this, just to keep it straight. So I've got right now my first thing is going to be my product. So I look at my products. Well, over here, taking a look at this, I've really only got one product. And so I'd say first thing, what's the coefficient in front of that? Well, the coefficient's 1, so I'm going to put a 1 right here. All right. And then I'm going to multiply that by the standard enthalpy of formation of C2H5OH. Well, I look at the table, but I've actually got them up here. So if I look, C2H5OH has a standard enthalpy of formation of negative 277.7. So I'll say negative 277.7 kilojoules per mole. Now, in this particular case, that is it as far as my product. So I'm going to end my brackets here, and I'm going to subtract off my next ones here. I'm going to drop it down just so I can use it a little easier. And so I'm going to say, now I'm going to look at my reactants. And so for my reactants, the first reactant is C2H4. The coefficient is 1. And so for C2H4, the enthalpy of formation is right up here, 52.3. 52.3 right there. But then plus, because I'm doing the sum of each of those here, adding them up, the next one, which is H2O, got a coefficient of 1 times the standard enthalpy of formation. It tells us of water is negative 285.8. So negative 285.8 right here. I can close that out, and then I can do my math. I want to combine these guys together, and so when I do that, I end up getting that, let's see, our reaction enthalpy, 1 times negative 277.7 is, of course, just negative 277.7. Then minus 52.3 times 1 plus negative 285.8. And if we add those up, I get negative 233.5. And so negative 233.5. And so negative 277.7 minus negative 233.5 is, of course, the same as adding 233.5. And so that tells me that our heat of reaction is going to be negative 44.2 kilojoules per mole. So we now have a way of figuring this out sort of from scratch. Every time we've had to figure these out before, they've basically been cases where we've had to look them up or be given information that'll do this. Now all we need is that table of enthalpies of formation, and we can use this application of Hess's law to figure out what this will be for any reaction that's out there. And so we can figure out whether any reaction is endothermic, any reaction is exothermic, as long as we have the enthalpies of formation for those substances that are used to make it up. Let's try another one. So in this case, we have SO3 plus H2O yields H2SO4. All right. Assuming these all are in their standard states, basically they will be unless I tell you they are otherwise. So for doing this here, we're going to set it up the same way we did before, is that to figure out this, we first want to sum up the products. And so we only got one product here, H2SO4. And so for H2SO4, there has a coefficient of just 1, so we put a 1 out there, times the enthalpy of formation for H2SO4. We look at our table here, it tells us it's negative 814.0. negative 814. Whoops, that should not be a decimal point right there. Let's try that again. All right, negative 814.0. And so then that's it for our product. So we're going to go on to our reactants. We're going to subtract off our reactants here. And so our first reactant is SO3. It's got a coefficient of 1. So we put a 1 out there times SO3, according to this, in standard state is negative 395.7. 395.7. And so plus, because we're doing a summation here, the water, we'll go once again a coefficient of 1, and then negative 285.8 still. 285.8. And so now we can go ahead and close these brackets off and do our math. And so whenever we do this, our enthalpy of formation, or our standard enthalpy change, is going to be just, well, negative 814 for our first one, right? And then minus, right here, we add these up. 1 times 395.7 plus 1 times negative 285.8. My decimal place has gone away there, negative 285.8. In doing that, I end up getting negative 681.5. So minus negative 681.5. And so once again, we're subtracting a negative, and so it's going to give us a positive. And so if we do negative 814 plus 681.5, and we end up getting negative 132.5 kilojoules per mole, and that is going to be our enthalpy change, our heat of reaction for this particular reaction right here. So one last example. So find the enthalpy change for the following reaction. SiH4 plus 2O2 yields SiO2 plus 2H2O. Setting up the same way we did before. We want to go ahead and look at first our products. So our products here are going to be SiO2. Well, we just have one of those, so the coefficient is going to be 1 times what is the enthalpy of formation for that? Well, I've got a table over here. So SiO2 is negative 910.9. So negative 910.9. Then plus, because actually we have two of them here, 2H2O. Well, here we have a coefficient that's 2. So I'm going to put a 2 in there times H2O. H2O is negative 285.8, because I think we've seen that every time here. 285.8. Close those brackets here, and we're going to subtract off of that our reactants. So our reactants are SiH4, and so how many SiH4s do we have? Coefficient's 1 in this case, so we're going to put a 1 out there times SiH4. Silane is going to be 34.3. And then we're going to add to that, because we're summing them up, 2O2, and so the coefficient is 2. O2, we look at it, has, delta HF of 0. Why is that? Because it's in its standard state. It's an element in standard state. O2 is what it is at 25 degrees Celsius, is a gas, and since it's in its standard state, that means the standard enthalpy of formation is 0. So now it's just a matter of, once again, doing the math on it here. So we look at this. This is going to be 1 times negative 910.9 plus 2 times negative 285.8. If we do that, I end up getting negative 1482.5. Negative 1482.5 minus, in this case, 1 times 34.3. And so that's just 34.3. So negative 1482.5 minus 34.3 is going to give me a total here of negative 1516. Negative 1516.8 kilojoules per mole. And that is going to be our final enthalpy change, or heat of reaction for this particular reaction. And so now we know that if we were doing, say, a calorimetry experiment, we could figure out how much heat would be gained or lost by the water, or figure out how much heat is released by the reaction in general.